a vector field is a function that assigns a vector to each point in space or on some domain. It might not be defined everywhere. So I talked a little bit about these in the lecture on differential forms. So in general, this will have the form f equals m x, y, z, I, so some function of x, y, z, another function of x, y, z for the j component, and another one for the k component. And we often use the letter f for such a thing because in many applications this represents a force. So this could represent, maybe we'll show an example first. So an example is the radial vector field given by 1 over root x squared plus y squared plus z squared xi plus yj plus zk. So this is not defined at the origin. Although you could do a variant of this where you didn't divide by the sides. So yeah, so some examples of vector fields are, this could be describing, for instance, the direction and magnitude of wind or water or some other fluid that's moving, or it could represent, a force like gravity or magnetic force, and so on. I should confess that in this picture here, what I've actually graphed is 1/2 the radial vector field. So I've divided all the vector lengths by 2, just because otherwise the vectors would start to overlap. And it's sort of very hard to read. So I'll just make a note. Whenever I'm depicting vector fields, I might scale them partly, mainly to make them easier to read, but also the direction is usually more interesting than the magnitude. I mean, the magnitude is important, but the direction of the vector is often, something more interesting to us, more important. So another example of a vector field is the angular vector field given by negative yi plus xj. So this is describing a rotation or swirling around the z-axis. And really this is, you can define this in 2 dimensions. So I could also view this as a vector field on R2, and then I've just sort of repeated this in R3. So where these, should mention where this angular and radial vector field come from. So in the differential forms lecture, I said del by del x is kind of the same as the constant vector I, the constant vector field, which is I everywhere. And del by del y is essentially the constant, the vector field, which is constant in J everywhere. And so then del by del R, so by the chain rule, this is del x by del R, del by del x plus del y by del R, del by del y. But x, so x is r cos theta, so del x by del r is cos theta, which is x over r. And so this becomes x over r I plus y over r j, which is, yeah, these are sort of the same thing. So that's the radial field we saw in the previous example. And then for this one, we would similarly have, for this angular vector field, this is del by del theta, is del x by del theta, del by del x plus del y by del theta, del by del y. Del x by del theta is negative r sine theta is negative y, and similarly, so this becomes negative y del by del x plus x del by del y, or again, these are sort of different names for I and j. A particularly important type of vector field is, so we can view the gradient So we can view the gradient of f of a function as a vector field. This is slightly different from the differential forms, the df that I discussed earlier, but not sort of, it's not that far off, but it's a little bit different. So here is an example of that. So f here is xyz is xy minus z squared, and the significance of the radial, or sorry, the gradient vector field is that, so the gradient vector field is normal to the level surfaces of f. So you can try adjusting the value of c on the slider, and you'll see that the so the fact that the gradient is pointing in the direction of greatest increase, sort of equivalent to saying that when you increase the value of c, the gradient vector field is showing you the direction that the level surface will evolve.